And here we go. We have liftoff. Propulsion continues to be normal.
RS-68 chamber pressure looks good.
Following up. Roger, roll, Atlantis.
Water towers, fly! Yes!
Tango down to nominal.
Flight downside FD off. Bring in FD off. Off. It's orange!
Oh my God! Oh my God!
Decollage. Look at that. Put that in the big bag,
343 unfolds to go.
Indeed.
We rise together, back to the moon and beyond.
This methane would be igniting with the flare, correct?
Yikes. You dead? We don't need any more of these.
Welcome, everyone, and hello. Welcome to our astronomy night. How's everyone doing out there? Yeah, all right. And welcome to everyone tuning in at home as well. My name's Alicia Siegel. I'm the producer of public programs here at the Intrepid Museum. And we are going to be having a really interesting conversation right behind me here coming up. So we've got a lot of fun stuff going on all night long. First of all, downstairs, you might have seen in Hangar 3, we've got education opportunities. We've got all these different activities. You can create your own spacecraft to touch the sun, just like the Parker Solar Probe. We've also got galaxy artwork you can make. We've also got planetarium shows downstairs. I don't know if you had a chance to check that out yet, but our friends from Parker Solar Probe actually have their very own planetarium show, so you too can touch the sun as well down there. Also coming up later on tonight, we're going to be having telescope viewing out on the flight deck. You can take a look at some of the stars up there. But of course, the main event here, we're so excited to welcome some experts from the Johns Hopkins University Applied Physics Lab. So everyone, without further ado, first of all, I'd like to explain what this is. We do this program called Astro Live. It's a free online program. You can check it out on YouTube. It's on the Intrepid Museum's channels as well as through our partnership with NASA Spaceflight. And you can check out old episodes as well, but most importantly, it's live streaming right now. So you are our live studio audience. Hello, everyone tuning in at home. But it's a really exciting opportunity to learn more about space. We can talk to experts and astronauts and all kinds of different things that are going on in the space community whenever we have these shows. So I want to introduce our guest tonight. I'm going to step on over here. There we go. All right, so right behind me here, we've got Dr. Noor Rawafi. He is an astrophysicist, a senior scientist at the Johns Hopkins Applied Physics Laboratory, and the project scientist for NASA's Parker Solar Probe mission. He's conducted groundbreaking research at institutions around the world and has authored and co-authored over 200 peer-reviewed papers. His extensive work portfolio includes a variety of solar and space phenomena, with a particular emphasis on the dynamic solar corona, including solar magnetic fields, coronal plumes and ejections, shock waves, and solar wind. If you haven't already gotten the idea, we're going to be talking about the sun tonight, everyone. We've also got with us Brian Rupert. He is a senior space systems engineer at the Johns Hopkins Applied Physics Laboratory and the deputy mission systems engineer for NASA's Parker Solar Probe mission. He served for 8 years in the U.S. Army as a Black Hawk helicopter pilot and conducted humanitarian relief efforts across the world, then left the Army to work at the Applied Physics Lab on NASA's Dragonfly mission, which also just got some exciting news recently. Congratulations. He's currently working on multiple NASA missions, as well as building a full-size model of Parker Solar Probe, which should be displayed in the National Air and Space Museum by this coming fall. Congratulations. All right, so everyone, please give a warm welcome to Noor Rawafi and Brian Rupert. Thank you, guys.
Thank you so much, and thank you, Lisa, for the kind introduction. I talked, and I don't know how many talks I gave about Parker Solar Probe, and I always enjoy talking about the mission. It's really the highlight of my career and my life. But there is probably no more exciting place than this one to talk about the space mission like Parker Solar Probe. We are just above us. We have the space shuttle. It's just fascinating. It's amazing. It's So I'm Noor Rawafi. I'm the project scientist. Brian is the deputy mission system engineer for Parker Solar Probe. we're going to tell you a lot about Parker Solar Probe, the technology, the science we are learning, the challenges, and a lot of stories that goes with this mission. But before that, when we launched Parker Solar Probe in 2018, the expectation and the enthusiasm about this mission were astronomical. Everybody is waiting for this mission. This mission, by the way, was thought of in 1958. I guarantee you that most people here were not even born back then. So we had to wait for 60 years for this mission to fly it. Obviously, the data we got from the mission were so exciting. There is a lot of new stuff but also we got images like these ones. And these images are not what we are looking for. These are not the corona, these are not the solar wind, these are not coronal mass ejections. What we are looking at here is basically debris from the spacecraft. The spacecraft is being bombarded by dust all the time. And whenever you have a dust hit on the spacecraft, you have a cloud of the spacecraft material that flies. And the cameras are basically recording that. So when we started getting these images in 2018, the first question that popped in our mind, how long this spacecraft can survive out there. The environment is so harsh, extremely harsh, way harsher than we thought. And we actually had a team to look into it. But the great news is, just a few months ago, on Christmas Eve of last year, Parker Solar Probe made history. It became the first human-made object that is closest to a star ever. That is our sun. If the sun distance, the sun-Earth distance is about 1 yard, Parker Solar Probe will be this close to the surface of the sun. That's what we say. Parker Solar Probe has touched the sun. Now I'm going to turn it to Brian, who will tell us a lot about the technology, and I will come later to tell you about the science. Brian.
Thank you. Thank you, everybody. So a little bit about the history of Parker Solar Probe. Nord was just talking about Eugene Parker. In 1957, he actually came up with the theory of the solar wind. And just a year later, President Eisenhower actually started and signed the National Aeronautics and Space Act, which really created NASA. Just a few months after that, NASA's doors opened for business. And just 3 months after that, there was an announcement, and I quote, "A solar probe to pass inside the orbit of Mercury and study the particles and fields inside the vicinity of the sun." That's when the solar probe was born, in 1958. And I don't think we realize how groundbreaking that was at the time. It's a little bit of perspective here. There's technology development, right, that happened after this time that we talked about this. Touch-tone phones, integrated circuits, Xerox copying machines, right? At this point, there had been 18 satellites that had ever launched, and only 8 of them had ever actually been successful. So you can see how bold this kind of mission was actually trying to be. And for all of you gamers out there, you can think of the most basic video game, Pong. That took 14 years after we talked about going to the sun before that was developed. So, that should put that a little bit into perspective. So what are some of the challenges going to the sun, right? One of them is the solar intensity. How hot are we feeling? And is the spacecraft actually being? So for solar radiation, the equation for that is 1 over the distance squared. Well, what does that mean? It means it's not linear. If I get a little bit closer, doesn't mean I'm getting a little bit more heat. I'm getting a lot more heat, right? So what you'll see in this graph here is that when you're at Earth, if you stood outside and you took out all the atmosphere, we'd call that about 1 sun, okay? As you get closer and you get to 9.8 solar radii, you're feeling about 500 times that. And that's what it's really hard to deal with. Other orbiters that you might be familiar with are Messenger and some other science. They're only around here at Mercury, so you can see that's only a very small fraction of what we're actually seeing on Parker Solar Probe. Other challenges that we have to overcome. We don't realize it, but while we're just sitting here, the Earth is traveling at about 30 kilometers a second. But to get to the sun, we actually have to slow down. So when we realize to launch, you have to gain energy, gain speed to get outside the Earth's gravity well. But then to get to the sun, you have to slow down immediately. Well, that's a big problem because we don't have any rockets available at this time to actually do that, even today. So what do you have to do? You could go to the inner planets, right? You could fly by some of those. We have enough, we call it delta V, or delta velocity, change in velocity, that we can get from a launch vehicle to get us into some of the inner solar system planets. But what does that do? You have to go, you get by them, they don't really give you a lot of energy as you fly by to slow you down. And so maybe you don't really get that close to the sun. Okay, that's one option. Whoops, I thought there was two things. The other thing that you could do is you could go out to the outer planets. You could go to Jupiter. We're all familiar with that kind of thing. As you go past Voyager, if you're familiar with those, flew by Jupiter and got a massive gravity assist. We could go by that. But Jupiter is the same problem as the 1 over distance squared, the intensity bit. It's colder out there. There's a lot less sunlight out there. And what it also does is when you come back in, you can come back in and you can get really close because it can slow you down a lot. But then you have the extremes of being super cold and then very, very hot when you get to the sun. So that's a big challenge that we had to deal with. So getting it right. I just talked about that slide. Sorry about that. So this was the original evolution of Parker Solar Probe. If you see here on the left, that's the probe as it was originally designed. You see this large triangle here at the top. This was a heat shield. They wanted it to be big enough that it could withstand the heat of the sun. But the problem here is that at this point, we were still thinking we'd have to go to Jupiter. And so you'd need really large solar arrays to keep it hot because heating your spacecraft takes power. Well, that's kind of hard because then when you get a little closer to the sun, it gets hot again. And then that might burn up your power source or your solar arrays because they're so large. The other thing you could do is you could put a RTG, or a radioisotope thermoelectric generator, nuclear power source on board that would heat you while you're at Jupiter. But again, we have the same problem as we get close to the sun. It's providing more heat than what the sun is. So we go through this whole evolution, and we're trying to figure it all out, and we get to about here in 2005, and we still realize that we just can't overcome the challenges that we're seeing right now. Until someone came up with going into the inner planets. And what we see is there's 7 gravity assists that you could get by going to Venus. And what that does is incrementally decreases the velocity that you have, so you get a little bit closer and a little bit closer each time you'd fly by Venus. And you can see here how far we were away. When we flew by Venus the first time, we got down to 36 solar radii. And now we've done all 7 of these, and now we're at 9.86 solar radii. Each time we do that, we're breaking our own record to the thing that's closest to the sun and the fastest thing in the solar system, man-made at least. And you can see right here, the economy of scale is very hard to understand. Like, what's $1 billion look like? I can't understand what 191 kilometers a second looks like either, right? Well, let's think about it. So it would take me from DC to here, it took about 3.5 hours in a train. It's about 2 seconds for Parker Solar Probe. Here to the moon takes astronauts about 3 days. It's a whopping 34 minutes. So then now that we know we could go to this interplanetary, we can do 7 Venus flybys, get a little bit closer, we get a lot of science going that way. We were able to unlock the design from 2008 to 2011 to be able to actually do this. And you'll see that big cone on the front here. We don't have that anymore. That was a big breakthrough, and that's what allowed Parker Solar Probe to continue on. And this is really the culmination of 50 years of study now at this point. And this is the development and the design change throughout that time, as you can see. And that's what we ended with in 2018, launching to the middle of the solar corona. So the major inventions, we had the thermal protection shield. We talked about that. It was a big cone to begin with, but now it's only 4.5 inches thick carbon-carbon foam that takes 2,000 or 2,500 degrees Fahrenheit or 1,000 degrees C on one side and 4.5 inches on the other. It's about room temperature. So that was a major innovation that went through this. Also, you have the solar arrays. Like I said, if you have big solar arrays, they have to see the sun. They're also going to get hot. So what we have here is we have retractable solar arrays that actually fan back and then come forward. And they actually need liquid cooling. So you have a liquid radiator that radiates out of these panels here, the black panels at the top here. It takes the heat from the solar arrays and puts it through there. What that does, though, it's only using 1 gallon of water. That's what cools these solar arrays. And then also we have to worry about how close we are to the sun, the autonomy system. If we go about 2 degrees off pointing, we actually get the TPS, or the thermal protection shield, doesn't provide the cooling that it needs, and we might actually get the bus outside and start burning it up. So that was also a really hard thing to deal with, is the autonomy system, to make sure that we did not burn up when we get close to the sun. Because as we get closer, it's all autonomous. We can't talk to it, and we can't do anything here from Earth. This is just a video of the thermal protection shield without the faceplate, the white faceplate on it. And you can see we're heating up one side, and you might notice the hand on the other side here in a second. That's NOR, and it's just room temperature on the other side. This is Parker being built. This is the bus as it starts. These are all the panels that go into it. We call that the bus. Then you bring in the harness, all the connections to make everything work together. Here's the fuel tank. Here's all the other stuff that's going on. Those are the radiators that we were just talking about, and everything coming together. You also have, here's them making the carbon-carbon foam TPS. Again, 4.5 inches takes you from 1,000 degrees C to room temperature. You can see the work that it took to do that. And that's the final TPS without the face sheet. This is Parker and its final build in a clean room. And then this is Parker in its full launch stack, ready for launch. And this is what it looks like when we're sitting here on around launch day. And at this point, we were still called Solar Probe Plus. But right before launch, NASA changed the mission to be called Parker Solar Probe for Eugene Parker. This is the first time that NASA has named a mission after someone who's alive. And he was able to actually make that launch. And for everyone, here's what the launch actually looked like. This will be volume, yep.
Status check.
Go Delta.
Go PSP.
Minus 15.
Roll for ignition.
10, 9,
This is start.
8, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff of the mighty Delta IV Heavy rocket with NASA's Parker Solar Probe, a daring mission to shed light on the mysteries of our closest star, the Sun.
Gives me chills watching it.
RS-68 look good in the full thrust mode.
So here's the full mission trajectory. This is where Parker, when we talk about getting closer and closer to the sun, this is what it looks like. And right here, as of April 7th, it was about here. Right now, today, it's almost at the top of its, the furthest distance away from the sun, about ready to go inbound on its 24th encounter. And now I'll pass it over to Noor to talk about some of the science.
Yeah. Thank you, Brian.
Thank you.
So while Brian was talking about it, it's basically around through the decade when we were developing Parker Solar Probe, and you relieve a lot of moment when you talk about it, and a lot of the issues that, when I say issues, these are big problems that basically the team has to overcome. But let me tell you a little bit of a story about the heat shield. The development of the heat shield actually preceded the mission itself. In 2001, NASA commissioned the Applied Physics Lab of Johns Hopkins to look into material that can serve as a heat shield. It took us a little bit over 6 years to come up with the right material and find a way how to build it. And it's then when NASA decided to go ahead with the mission. Without that heat shield, we would not have a Parker Solar Probe. It's very simple. So, the other thing about the launch, obviously, I went down there to the Cape to see the launch, and oftentimes I'm asked, did you enjoy the launch? I did not enjoy it. And the reason is pretty simple. You spent so much time on this mission, and it's a mission that we have been waiting for 60 years, and the only thing that you're hoping for, just bring it up safe and leave it safe. So it was amazing. Now I enjoy it when I see it, but back then I did not enjoy it. So you might ask yourself, okay, why do you spend decades and decades and a lot of money you spend to go so close to the sun? Why is that? One of the very simple reasons that we want to understand how the sun works, because we are connected to the sun. The sun can affect us in so many ways. And I will give you some examples for it, which is what we call space weather now, and I will show it a little later. But when you talk about science, there are certain phenomena that we know about the sun. They are mysteries. They were discovered decades and decades ago, but we don't really understand them. And these phenomena are not unique to the sun. They are true also for the billions and billions and trillions of stars out there in the universe. So understand how the sun works helps us here on Earth, but also helps us understand what is out there as well. The first phenomenon is what we call the coronal heating. When you look at the surface of the sun that we see with the naked eye, the temperature is about 10,000 degrees Fahrenheit, 6,000 degrees Celsius. You move about 3,000 kilometers above, and the temperature of the gas, all of a sudden, will jump to more than 1 million degrees Celsius, which is about 2 to 3 million degrees Fahrenheit. The big puzzle, we don't know how that is happening. And the other big mystery as well is that from everyday experience, if you have a heat source, the further you move away from it, it cools down. But obviously, this does not work for the sun. We know that the energy is coming from the interior of the sun, but when you move up, it gets hotter. And that's really a big mystery. And as I said, this is not unique to the sun. It's also, you see it in billions and billions of other stars out there. So obviously, when you have that boiling gas at multi-million degree hot, it does not stay static. It flies away. And what it does, it creates a flow of particles that are electrons, protons, and heavy ions that constantly leave the sun to fill the whole heliosphere. That's what we call the solar wind. And you cannot believe it, that every second of our lives, we live actually in that flow. The reason we don't feel it because we have the magnetic field around us. That's the only reason what we don't feel. But the mystery about this one as well is that when you look very close here to the sun, the particles are almost static. Their speeds are about 10 kilometers per second. 10 kilometers per second for here is really big. It's large. But out there in space, it's nothing. Over a very short distance, let me go back to this one. Over a very short distance, they will start flying at hundreds of kilometers per second. And there again, we don't know where they get the energy from. I think the big one, I think every one of you should be familiar with. In May of last year, we have that big storm that caused the aurora that probably some of you have enjoyed. That's actually the making of these explosions on the sun that we call flares and coronal mass ejections. And whenever we have one of them there, they send a lot of magnetized material our way. And when you see the snow shower, that when the movie comes back, these are actually particles that are flying at almost the speed of light. And when they hit the detector, they leave a track there. And this is actually what is the big hazard for astronauts, for technologies out there. This is actually the particles I'm talking about. This is actually the thing. We want to understand how these particles are being accelerated to almost the speed of light. And the reason we want to understand that will help us to help astronauts and also to safeguard our technology out there in space. So these are the big three things that we want to understand about Parker Solar Probe. But I'm going to share with you the very first discovery that we made with Parker Solar Probe. It has absolutely nothing to do with these three phenomena that I talked to you about. It's about something totally different. And this dates back to 1929. It's almost a century old now. There is a physicist called Henry Russell. He was looking at stars out there in the universe, and he was studying dust around stars. And he came up with a theory basically saying that in the immediate vicinity of the star, there should be no dust at all. It's basically there should be a dust-free zone. And the reason for it is that these micron-sized dust particles, when they get very close to the star, they get heated so much, they basically sublimate and they will be washed away by the radiation pressure. Obviously, astronomers, they turn to the sun. This is the closest star to us, and they look for evidence for this dust-free zone. For decades and decades, there was no evidence for it whatsoever. When we launched Parker Solar Probe, we thought that toward the end of the mission, which is about now, the end of the prime mission, that we will get some evidence for it when Parker Solar Probe is so deep close to the sun. But from orbit 1, Parker Solar Probe showed us the dust-free zone exists around the sun. It solved basically a big mystery out there for us. Now, and this is another one. So when we from previous missions, whenever we launch something in space, and you measure magnetic fields, temperatures, densities, we are used to fluctuations small like these ones here. When Parker Solar Probe got close to the sun, and this is the distance to the sun, we started seeing this in the magnetic field. That was a scary moment for us, because the first thing that came to mind, we have problems with the instruments. And guess what? If you are waiting for 60 years, and the first thing you get is you have problems with the instruments, it's not a good feeling. And what adds to it, this is actually, we looked at this data on a Tuesday. On Thursday, we were supposed to share the data with the public for the first time. Basically, we had 2 days to deal with everything. I remember somebody in the audience, we said, for God's sake, we don't need this now. But guess what? It took us about 10 to 15 minutes, did some checks on the data. These are physics checks, and everything checked out. What we are looking at here is something new that we did not know before. And what are these? Basically, when you look at the magnetic field close to the sun, it has folds in it. Basically, it rotates all the way back to the sun and out again, making an S shape, like a switchback. And by the way, we call them switchbacks. And yeah, it's like this. And the funny thing about them, close to the sun, you have a gazillion of them. The other nice thing about them, they carry so much energy with them. And guess what? If you want to explain the heating and the acceleration of the plasma, what we are looking for are energy sources that we didn't know. This actually could be one of them. Let me give you one thing about it. This is almost one perfect switchback. What you are looking here is the magnitude of the magnetic field. This is one component of the field. It basically changes polarity from 100 nanotesla to minus 100 nanotesla, basically saying that the field rotated all the way back and out again. But the important thing is this. Look at the velocity of the plasma. Here it's about 300 kilometers per second. Here it's almost 700 kilometers per second. So these things, they pump energy into the plasma. And that's what we want. But obviously there are so many things that comes with them. There are mysteries that comes with them. We don't understand where do they come from, how do they form, and how do they evolve to release all that energy to the plasma, to heat it and accelerate the plasma. And trying to understand them, basically by dissipating all that energy, we basically solved a problem that has been around for almost 30 years now. That solar wind, when it is expanding out there, it keeps being heated and accelerated. And that one now we understand thanks to this new phenomena that we actually discover. That is the switchbacks. The other big problem about the wind is the sun is really massive. And the gravity of the sun is huge. The big problem for us is how these particles manage to escape the gravity of the sun. They need a ton of energy to escape it. Now, what we thought about this solar wind before, we thought it's basically like water vapor. You heat the plasma and it will evaporate slowly to escape the sun. But trying to understand the switchbacks changed completely everything for us. So what we were looking at, that one basically. Now, when we look at the sun here, lower down, what we are seeing is that the solar surface acts like a shower head. Basically, you have very tiny explosions all over the surface of the sun, and every one of them will give you a jet of plasma, a very small jet of plasma that is extremely hot, but it's also very impulsive and fast from the get-go. This is how now we think the solar wind is forming. It's not that vapor anymore. It's basically impulsive events that are very tiny, but collectively, when they move out there, they will form the flow that we measure around the wind here. And the physics of this is totally different from the physics that we have been dealing with for the last 30 years. So Parker Solar Probe is not only helping us to understand, it's also changing the physics for us. And that is quite fascinating. Yeah, by this, I think I personally believe we are only maybe 4 to 5 years to close these two big problems that are the heating, the acceleration of the solar wind. You know, by the way, the discovery of the heating of the corona was on the late 30s. And the discovery of the solar wind was in 1962. One of them is over 80 years old, and the other one is over 60 years old. Parker Solar Probe now is going to almost close them forever. But the big thing is, whenever you close a science problem, what you do, in fact, is actually you create a big problem that you have to deal with it in the future. Now, the big question for us, what is the other big phenomena that Parker Solar Probe is going to discover that will keep us occupied for the next century? Like the coronal heating, like the solar wind. Can you please make it as loud as possible? I'm going to play, let it play again, and then I'll tell you what we are looking at. Okay, so the sun that we see with the naked eye is basically a ball of gas that is very gentle, doesn't do anything. But in reality out there, the sun is extremely active. And this is one of the humongous coronal mass ejections that was launched when Parker Solar Probe was very, very close to the sun. This CME was, coronal mass ejection, was traveling at more than 2,500 kilometers per second. That was in September 5th, 2022. And the funny thing, when this hit Parker Solar Probe, it was actually on the backside of the sun. And for days, we did not know whether Parker Solar Probe survived the event or not. We knew that it hit Parker Solar Probe, but because it is on the back of the sun, and as Brian was saying earlier, we cannot talk to the spacecraft anyway. We have to wait for it until it emerges on the other side to see how it did with it. But obviously, Parker Solar Probe is a marvel of technology. It dealt with it without any issues at all. And the data we learned from this is just mind-boggling. One of the things that we learned from these images, if you will see some of them later as well, that we have been observing this coronal mass ejection for decades now. And we thought we understand them. We understand the structure of these events. But when you look at the complexity that Parker Solar Probe is showing us, it's basically we didn't get that before. Now we have another problem that we have to understand where that complexity is coming from and what it does to the environment that it's flying through. But there is one thing that it did, this event in particular, and there are others as well. They basically swept everything in their way. They left nothing behind them, almost like a perfect vacuum. All the plasma, all the gas, they were swept away. Even the heavy dust particles, they were also swept away. That is something we didn't know about then. So it's no-brainer when one of them hits our atmosphere. They cause all the havoc that we see every now and then, because they are so violent by nature. Let me show you some of the data that what we got from the closest approach of Parker Solar Probe. When we think about the sun, most of the material is always flying out. Sometimes you see hints of probably some material coming back. When the movie plays again, focus on this one now. Look at all this such material that is flying back, following back to the sun. We don't really understand what causes that and what it is in the first place. This is so new to us that we haven't seen it before. First of all, we understand what causes it and how it evolves and what it does to the rest of the atmosphere down there. And when you look also at all the flow that is going on here, there is a myriad of structures that are basically colliding on top of each other. I'm going to show it to you better in the next movie. Look at the CMEs here. There is one here. There will be 2 or 3 more. And this one, next one, look at them, how they are colliding and basically deforming completely. This is what we call coronal mass ejection cannibalism. They collide and they kind of eat each other's. But now we have a big question to us. How that dynamics is being done. Whether it's done through the magnetic field or it's done like fluid. That's an open question to us that we have to deal with. When it comes to the acceleration of particles, I forgot to tell you that when these big events, like the one I showed before, actually we want them. We want the sun, when probe is so close to it, to unleash the strongest events ever. Because those events are the ones that will teach us how the particles are almost accelerated to the speed of light. And by the way, this image doesn't look very nice, but this is how we measure the particles that are almost flying at the speed of light. And what we are used to is basically a slope like this one here. And what this slope tells us that the particles with high energy arrive to the spacecraft before the slower ones that arrive later. That's what we call dispersion of particles. The first one will come to you before. Parker Solar Probe shows us also another dispersion in the other direction. And this is exactly what we have been looking for, is to fly through the sites where the particles are gaining that energy. These are the shock waves. These are the shock waves that we wanted. So how this happens you will have tiny explosions that the magnetic field with opposite polarities comes together, and basically they cancel each other. Once they cancel each other, they release the energy to the plasma. And that's how it's done. That's what we call the magnetic reconnection. I told you a lot about the sun, but Parker Solar Probe is way more than that. This is not the sun. This is Venus. Obviously, we use Venus to get closer to the sun, but when we are flying by it, we turn all our instruments on, and we want them to measure the environment of Venus. And Parker Solar Probe made discoveries that was really unprecedented. Let me tell you about this. When we look at the surface of Venus, there is thermal emission that is coming from the surface of the planet, and it has a wavelength. And this is the history of the discovery of these wavelengths. In the mid-80s, we discovered the 2.3 and the 1.7 micron. In the early 90s, Galileo discovered the 1 micron. Cassini in the early 2000s discovered the 0.85 micron. Parker Solar Probe now holds the record of the shortest wavelength thermal emission from the surface of Venus. That is 0.7 micron. What Parker Solar Probe did is basically opening a new window to study the surface of the planet. Not only that, it's actually telling us about the geology of the rocks on the surface. And this is not a mission that is done for a planet. It's done for the sun. But still, we learn so much from it. About the future of the mission. Obviously, we launched here in 2018 when the sun was very quiet. We did all this. Now we are at the solar maximum. The nice thing about Parker Solar Probe is it's so healthy that now we are going to cover the rest of the solar cycle until we get to the minimum. Basically, we will close the whole solar cycle, and hopefully after that, the mission will keep going. Because, as I said at the beginning, the environment is extremely harsh, but still now, the spacecraft is really healthy. Let me tell you this, and I see a lot of young folks here in the audience, and this is really great. About 120 years ago, the Wright brothers realized the very first human flight. And you can go how much hardship they went through to realize that. In 1969, we landed the humans on the moon. On Christmas Eve of 2024, we touched the star. But the important thing, the quest continues. And it will continue with folks like you and you and you and you. Thank you very much.
All right. Does anyone have any questions for our guests tonight? Please raise your hand up, big and tall. I'm going to come around with a microphone so that everyone can hear you. All right, right up here in the front.
Hello. Could you tell me something about every 11 years has to deal with the sun?
Yes.
The activity?
Yes. This is exactly what we are talking about. This is what we call the solar cycle. So when we are at the minimum, when you look at the sun, you don't see too many sunspots. The sun is very quiet. Go ahead, please.
Is this where Aurora Borealis would be more active?
Active now. The Aurora Borealis will be active more at the maximum of the cycle, like now. Yes, like now. Here we see them every now and then, but they are rare. Because the aurorae are caused by these coronal mass ejections that I was showed earlier, and we see a lot of them at the maximum rather than the minimum. Yeah.
Other questions in here in the front?
Why was the shortest wavelength of most interest for Venus?
All of them are very interesting. But what is this? This new wavelength is new to us. It's basically another window to look at the planet and to study the planet. It's like you have a house and you have several windows. If you open another window, it will give you another view that you didn't have before. Yeah.
Okay, back here.
Hi, I was wondering what the lag time was between Earth and the Parker Solar Probe, and does the sun rotate? And I have to say, under neath the shuttle here. I'm a Coast Guard veteran, and it's a little-known fact that whenever the shuttle is flying over a body of water, the agency of jurisdiction is the Coast Guard. I was stationed in Honolulu, and I was an operations watchstander for the shuttle missions. So thank you very much. That was a great presentation.
Thank you.
Yeah, so the round trip light time question that you had. Yeah, it depends on where it is, because the Earth is going around the sun, and Parker is actually kind of staying in the same orbit, like this way, right? And so when you're on the far side, it's going to be, maybe we can, really long, right? And I think we're at about two and a half minutes now, I think, is the round trip lifetime.
Yeah, about, yes.
And I think I can't remember the furthest.
Okay, let me give a ballpark here. The light will get to the sun, to Earth, in about 8 minutes and a half. So when Parker Solar Probe is really on the other side of the sun, you can double that, but it's actually less than that because it's never at 2 AU. So it's between, as you said, about a couple of minutes to something like 13, 14 minutes. It's in this range.
Does it rotate?
The sun rotates.
The sun.
Oh, yeah, absolutely, yes. Well, the sun rotates. Everything out there rotates. Everything, yes. Yeah.
Okay, right.
And the funny thing, let me add this. When probe is flying around the sun, obviously when we are far away, it rotates slower than the sun. But it gets closer to it, it becomes really rotating faster and faster and faster. At a certain point, probe is actually rotating around the sun faster than the sun is rotating around itself. And after that, when it moves out, it slows down again. Yeah.
Okay, right over here towards the center.
Okay, so this is like an odd question, guys, but say if someone was dealing with like an unclean spirit, as in a sort of possession, and they were in space and they needed to be delivered, and it involved some sort of mind control. If you guys have education about how it is when it comes to possessions and demonic entities and how they talk about they have abilities and they're able to affect the brain, how would you be able to go about that, like from there about that?
I don't know anything about it. So.
Me neither, honestly. I have never. I never thought about it, and yeah. So thank you for the question anyway. So we'll think. Yeah.
Sorry.
Thank you. Thank you.
Hello. Hello. I have a question. I noticed in the building of the Parker, there was some pictures of people wearing hair nets and gloves. Why is that?
Yeah, when you do, as you're building a spacecraft, you want to keep it as clean as possible. Any imperfections in the spacecraft, anything that's on there could actually damage it even during operations. So we want to keep everything really, really clean. And that's why the whole thing is built in a clean room. And even if it's not, then we take it through a special process to bake it, heat it up really hot or for a really long time, get all that dirt and stuff out of it, and then cool it back down, and then we put it into the clean room. So that's why we do that.
Okay, in the back here?
Yeah, you mentioned before that the probe that you put around the sun, when it goes behind the sun and Earth is in front of the sun, you have communication issues, right? Because the communication can't go through the sun. Is there a solution for that? I mean, could you put satellites maybe orbiting around so that they can like ping that signal around? Or is there a logistical reason why that doesn't happen?
Okay. So by design, Parker Solar Probe, when it gets close to the sun, we don't talk to it. And that's why, Brian, when he talked about autonomy, Parker Solar Probe, when it is down there, it has to be 100% autonomous. Meaning that it encounters certain problems, it has to solve them by itself. We cannot do anything to it. So whether it is on our side, on the other side, we are not going to talk to you. Just deal with everything by yourself. When you get out, we'll talk. That's how Parker Solar Probe is designed. For other missions, there are thoughts to put a spacecraft that is permanently stationed on the backside of the sun. And as you said, obviously we cannot talk to it. So what you have to do, you have to have a relay satellite that will talk to that mission over there, and the relay satellite will send us the information. But for Parker Solar Probe, by design, wherever it is, when it is close to the sun, we don't talk to it.
Why is that?
And there's also a part to that, Nor, about as we're close to the sun, because we can't off-point, our antenna is only pointed, where are we? Here we are. There we go. It's only pointed in one direction. So as we get really close, there's only a small percentage of what we would see, and the Earth's usually not in that small area, and we'd have to off-point to get there, and then we'd burn up. So that's another reason why we can't do any of that during the actual closest approach.
Thank you.
Yeah.
Any other questions? Yep, right over here. Oh, a few of them. Great.
Hi, thanks so much for sharing all that. Really super interesting. My question is a little bit more personal, so I'm curious what sparked your interest in astronomy, and when you were younger, what are some things that you did or wanted to learn more about that I guess we could learn a little bit about.
So when I was younger, something for sure I knew about. So I liked math. I like math, I like science. I knew that I want to go into research, but what research? I think the thing that was interesting to me, there are two things, is quantum optics, because I like quantum mechanics so much, and I liked optics too, so I want to combine both. And the other thing is particle physics. And guess what? I was accepted in both. And at the end, I changed to do space physics. It's really a last-minute change that I did it. Do I regret it? No. This is probably the best thing I ever done. But my interest in space dates back to when I was really a kid. I was a child. I was born in the countryside. And the nice thing about the countryside, there is no light pollution. And in particular, summertime, you looked up there, and my goodness, it's amazing. I remember as a kid, I was trying to count stars. Obviously, you cannot count them. There are so many of them. The other question that comes to you is what is going on up there? And are there people living there? And guess what? That question of a child is actually a fundamental question that is at the top priority of NASA and the other space agencies. If you go to the NASA website, the first question is, are we alone in the universe? And guess what? Every one of us, when we are born, we ask ourselves these questions. Whenever you look out there in space, are there people living there? And that's basically the same questions. Is there life out there? So, in a way, when we are born, we are born explorers. We live as explorers. And we live this life as explorers as well.
Brian, did you want to answer that question too? How you got into it?
Yeah, so, sort of like Nora, I just liked looking up into the sky for a long time and just loved the moon, always the first thing. And then just seeing these launch and actually seeing operations like that, it always made me want to do the space stuff after, when I grew up. So that's it, yeah.
All right, over here there was a question.
So, practical question about what you've already observed with this probe. You mentioned the switchback phenomena and the kind of the showerhead dispersion phenomena. If you were to visit again, what would you look for to confirm what's causing? Like, what kind of sensors come to mind if you wanted to try and uncover what's causing that phenomena? Do you have that in mind already?
Scientists are never short of ideas. We always want to look at stuff. So I think one of the things is getting closer to the sun would be helpful. What I showed earlier, closing the solar cycle, also showing observing all these changes will be extremely helpful as well, because it shows you different phases of the sun and will point you to the sources of everything that the sun is producing. That will be helpful as well. But for a mission like Parker Solar Probe, if there is anything I wish we had on probe, but in the future we definitely have to do, there are certain type of measurements that you can do only when you are close to the sun. And some of them have to do with gamma rays and the solar neutrons. And in particular solar neutrons, there is an issue about them. They decay so fast. The sun produces them, but very soon they will decay. So they will not arrive to us here. So an instrument on a mission like Parker Solar Probe, like that one, would be fantastic, would be amazing. And obviously there are, for example, I talked before about the dust. What we are using now, using the whole spacecraft as a dust detector. Because when a dust hits the probe, we have the antennas. It tells us basically what direction it's coming from, but it gives us also the energy of the impact. But we cannot say what is the mass or the velocity, because the energy is the combination of the two. Having a proper dust instrument would be also another amazing thing. But there are so many other type of measurements that we want to do. So yeah, it's, yeah. Mm-hmm.
Okay, any other questions? Oh, yep, over here. A couple more.
I'm very interested in the universe, astronomy, just generally speaking, astrology as well, the 12, what are they, the constellations, the signs. You have like Gemini, Cancer, for example. All that astronomical bodies, right? The astronomy and astrology. For me, there was a new one, a 13th. Is that something that you guys believe in? Is that something that is true? That there's a 13th constellation, a 13th sign of the stars in the constellations?
But in terms of constellations, let me first of all say why there are 12. But first of all, I believe and I live astronomy. I don't believe astrology, the other part of it at all. I don't believe it because that's, to me, it's not science at all. But let me tell you what is the 12. Why there are 12 signs. There are, when you look at the orbit of the sun, as seen from Earth, across the year, every month it will be within one of those constellations. It basically, we don't see this constellation on the sky, and that's why there are 12 of them. It has to do just with the orbit of the sun. Every time it will be within one of those constellations. But when you look out there are gazillions of constellations. Constellations basically families of stars that come together. The 12, they are related to the orbit of the sun, but for science there are plenty of them out there. It's not only, these 12 are not, from scientific point of view, they are not particular in any way.
Okay, and our last question right over here.
Thank you. Question on imaging. When in the video that they were showing that was close by, how you even capture that video? I mean, you're so close. There's so much energy. So are you using a super narrow band filter, or how do you do that?
No, this is only white light imagers. And the funny thing, actually imager is this one here. And if you imagine the sun is on that side, the TPS has to protect the spacecraft from the sun. We can only look at on the side of the sun, and we see all that material that is coming our way. But it's just a white light camera. That's what it is. It's not something. Yeah. Are we? Yeah. Can I? We have an engineer here. Well, plenty of them. Well, he's an engineer, okay. But we have the youngest engineer here. That one. Can you please come over?
Look at this little guy.
Oh, look at this. Go around. Come around. Come around.
This.
Okay, tell us what you built. What did you build?
I made the Parker Solar Probe.
There you go.
This is the sun shield. These are some of the antennas. That's the cup.
Yes.
And this is an antenna that keeps falling off. It's a
That's fantastic.
And that's the body.
I mean, you should be really proud of him. Really
a round of applause for that.
Yes, absolutely, yes. You know Parker Solar Probe better than me. Yes, absolutely. Thank you very much.
He's starstruck. Look at this.
Absolutely, yes. Yeah.
Great job, buddy. That's
all right, thank you, my
model.
friend. And let's get you down the stairs. All right, well, everyone, put your hands together one more time for our fabulous presenters here from the Johns Hopkins University Applied Physics Laboratory working on the Parker Solar Probe. Fabulous. And thank you all so much, everyone, for tuning in at home, too, if you're not with us. Also like to give a special shout-out here for our ASL interpreters who've been joining us tonight, so thank you for that. For those of you who are here on site, we still have lots of stuff going on. Of course, if you are fascinated now, as I am, by the Parker Solar Probe, go downstairs, check out their planetarium show. They actually have a special one just for this mission, and you can experience what that's all like touching the sun. Very exciting. We've also got over in the table right back there, they're going to be sticking around. You can ask them more questions if you'd like. You can find out more information about the Parker Solar Probe. Really cool handouts and stuff back there as well. Of course, we've also got our education activities downstairs. You can make your own little Parker Solar Probe just like that. And in a little bit, we are going to actually I think they're starting already. We've got telescope viewing out on the flight deck too. So if you want to check out some of the stars, might be a little cloudy tonight, but you can still check it out and see how those telescopes work. But everyone, for those of you tuning in at home, if you're watching via the NSF channel, stick around because we'll be debuting our newest episode of This Week in Spaceflight. And otherwise, if you're not, thank you for tuning in. And we hope to see you back here for another time here at the Intrepid, another astronomy night perhaps. Our next one's coming up in July, and we are so excited. We're going to be hosting some members of the Polaris program, some of the astronauts from that. So be sure to come back and check that out. And otherwise, we hope you have a wonderful rest of your night. Come check out the Intrepid sometime. Thanks.
And here we go. We have liftoff.
Propulsion continues to be nominal.
R68 chamber pressure looks good.
Following up. Roger, the planet.
Water towers, fly! Yes! Tango down to nominal.
Flight downside, speed off. Bring in, speed off. Off. It's orange!
R25! Oh my god! Oh my god!
Decollage.
Look at this!
Put that in the big bag,
343 unfolds to go.
Indeed. We rise together back to the moon and beyond.
This methane will be igniting in the flare, correct?
Yikes. Keep that. We don't need any more of these.